Welcome to the Alpha Training and Consulting's online training program. Today I'm going to answer the question, what is a chi-squared statistic, also known as best of fit? All right, let's get started. The T statistic, Z statistic, and F statistic all assume the data that we use to perform the test is from a normal distribution, and as a result, they're referred to as parametric tests. Parametric tests. The T statistic, Z statistic, and F statistic are tests that use variables data. Also, if it's normally distributed, it's going to use variables data because variables data creates continuous curves, which the normal distribution is one. All right. Now, we're going to do a different test today. It's not going to be a parametric test. It's going to be our first non-parametric test that we talk about. And so what does a non-parametric? Well, if parametric means assuming a normal distribution, non-parametric means it's distribution free. Doesn't care what distribution it comes from. Now, granted, it still needs to be predictable and measurable as always. We always need to make sure that's the case before we do math, remember. So here it is, the mathematical formula for the chi-squared statistic for qualitative data, or in other words, a non-parametric test, is listed here. Chi-squared equals the summation of observed minus expected squared divided by expected, which will mean nothing to you until we go to the contingency table and show you how this formula works. You're going to find out it's not really that bad. Like our other inference statistics, the critical chi-squared statistic is found in a table. This is the chi-squared table right here. And notice it has alpha risk of 5%, 10%, 90%, and 95%. Notice this is not symmetrical. It's skewed to the right. The chi-squared distribution is. The chi-squared distribution is traditionally known, or better known, for modeling variance. Modeling variance. The F distribution is used to model ratio of variance. And so this is for variance traditionally, but we're going to use it in a unique non-parametric test. Now, what does this 5% mean? Well, you start at the right of the distribution, you head your way over. So 5% alpha risk means 5% of the distribution lies to your right. Okay, and if you go over here to 10%, that means 10% lies over here. If you go clear over here to 90%, it means 10% lies to the left. And if you go to 95, it means 5% lies to the left. That's not really going to help us today, but I just wanted to introduce you to a new fact that we haven't discussed yet, and that's a non-symmetrical curve. But today we're just going to use the right-hand side of these two right-hand columns. It's a right-tailed test is what we're working on. All right, let's move forward from that. We will now perform an example problem using the chi-squared statistic for attribute data, in other words, non-parametric test. Let's assume you are interested in determining if a difference exists between your inspectors in a glass factory. So here we have, to determine if a difference exists, you let each inspector inspect a sample and record the number of defectives found. So you set up this test and you have a big pile of product, big box of product, and you happen to know, because you planted in there 60 bad parts, and you want to see how well these inspectors do. Okay, so inspector 1, as you see here, defective detected was 56. Okay, out of 56, or out of 60, they found 56 of the bad ones, which means 4 went undetected. Here's inspector 2, 57. They found 57 of the 60, which means they let 3 go. The third inspector found 53, in other words, they let 7 go. Now this is called a contingency table in the world of chi-squared. Yes, a contingency table. And these are the observed values. This is what we observed. As you recall, that equation has observed value there. That's the observed value. You ran an experiment and you observed a given outcome. Now, just so you know, this contingency table, we'll need to know this later, there's 2 rows. You don't count the rows of doing the math. And 3 columns. So 2 rows and 3 columns on this contingency table. Determine with a 95% confidence level, or 5% alpha risk, if a difference between the inspectors exists. Look up 5% as chi-squared contingency table problems are always right-sided and one-tailed tests from the tabulated perspective. So just know it will, in this case, you never split alpha risk in two. In other tests you will, but not in this one. First we need to find the critical statistic. So remember, this is the degrees of freedom, by the way. Number of columns, -1, rows, -1. And just a reminder, how many rows do we have? 2. How many columns do we have? 3. Okay, with that being said, let's go back here. Columns, 3, -1 is 2. Rows, -1. We had 2 rows, so 2 minus 1 is 1. Now sometimes you just have 1 row. If you do, you don't worry about that. You just use columns -1. But in this case, we have a degrees of freedom of 2. So let's go to that table and find out what our critical statistic is. Here it is, degrees of freedom of 2. Remember, we go over to the 5% column. There it is. And we had a critical statistic of 5.99. 5.99. Now this is our critical statistic. Then we're going to calculate a statistic. We're going to compare the two and decide if there's a statistical significant difference between these inspectors. That's the way. I know I haven't lectured that way. I've always lectured on p-value and alpha risk, but today I'm going to compare 2 statistics. It's a little bit of a different methodology of getting to the same place. So here's my critical. Then I'm going to get my calculated here in a little bit. But remember 5.99, the critical statistic is equal to 5.99. The next step is to calculate the chi-squared statistic. To do this, we must first calculate the expected values. Here's the formula for the expected values. Now the expected values will be the same across all these because this bottom row has the same total number. Okay, just so you know. And when they're all the same number, you could just take the average of all these. When it says expected value in statistics, that's usually what they mean is the average. The average is the expected value. But in some cases, these columns don't add up to the same value. In that case, you have to use this formula. I just decide to use this formula all the time because it's less confusing to students. All right. So the expected value that we have to calculate, remember in that formula is observed value and expected value. So we have to calculate an expected value. This is how you do it. Row total, which the first row, I'm working on this cell, by the way. I'm trying to get the expected value for this cell that has 53 in it. The way I do that, I take the row total, the row that number's in, and that's 166, times the column total for this cell, remember, 66, we'll go here, or I'm sorry, 60, I don't know where I got 66 from, 60, okay, and divided by the grand total, so you add all these together, you get 180, or you add both those together, you get 180, so that's called the grand total. I put that in the denominator, I crunch the numbers, and I get 55.33, and I always, it's pretty common, to put the expected value in parentheses. So this is the expected value, this is the observed value. All right. Then you do the same thing for every cell. Call it row total, 166, times column total, 60, divided by grand total. Same thing we did last time. In fact, they're the same numbers. Why? Because the column total and sum total are the same on all these. So I'm just showing you again. And then I do the same thing for the next cell. And I get 55.33. So you can see in my contingency table, in parentheses, that's my expected value, and those are my observed values. Now let's go ahead and do the same thing for this second row. Notice the row total is different. The first row had a total of 166. This total of this row is 14, so that's going to change everything. Anyway, I plug in my numbers just like I did last time. There's my row total, column total, grand total, and it gives me 4.67, so I put it in parentheses. Well, guess what? All the row total and columns are the same value, so all of these are going to have a expected value of 4.67. And here's my completed contingency table. For every cell I have expected and observed, etc. So now I'm really ready to start doing the mathematical analysis. And here we go. Remember, chi-squared is observed minus expected squared divided by expected. There it is. This is observed. Goes right there. Observed minus expected. There's the expected squared divided by expected. So expected shows up in two places in the formula. You put it here to find the difference, and down here in the denominator. And I do that for every cell. And notice it says add them all together, so I'll be doing that. But I have to do all the cells. I just did the first three because I didn't have enough room. Okay, and then I crunched those numbers. I crunched every one of these series. And I got 8 thousandths for that one, 50 thousandths for that one, 98 thousandths for that one. Now I still need to do the lower section here. So here I go. Observed minus expected squared divided by expected, just like the formula says up here. It says sum them all together. That's what I'm doing. So I do there's the observed, expected, so you should be comfortable with that. You may want to do this manually to get more comfortable with it. And I do all the math, and 96 thousandths for that series, 59.7 thousandths, and 1.163 for that one. Okay. Now I put them all together so you can see how I did this. I did all three of those, 1, 2, 3, and all three of these right there. I crunched all the numbers, I added them all together, and I get a chi-squared of 2.012. So that's my chi-squared calculated. All right. So, in summary, my chi-squared calculated is 2.012, and my chi-squared critical is 5.99. Since chi-squared calculated, right there, is less than chi-squared critical from the table, we do not have enough evidence to reject the null hypothesis. In other words, for this problem, we do not have enough evidence to say any of the inspectors are different. They are statistically insignificant. The null hypothesis, all inspectors are equal, and we haven't really got into null hypothesis and alternatives, so even though I talked about it here, I'm not worried about it. Just know, in this case, for this particular calculation, if chi-squared calculated is less than chi-squared critical, then they are statistically insignificant. If the chi-squared calculated was more than 5.99, let's say it was 10, and this is the critical, then I would say there is a statistical significance. But since our critical, our calculated was less than our critical, we would say there is no, it is statistically insignificant, the difference between those three operators. In other words, we can change them around, do another test that you'll see the one that finished last this time would be maybe second or third. They'd always go back and forth because they're statistically insignificantly different. All right. Now they also call this the best of fit. Best of fit. Chi-squared you use for best of fit for usually non-normal distributions. So you can see from a set of data, is this come from a binomial distribution or does it come from a chi-squared? Those are two that are commonly used for, Poisson and binomial. But how does that work? Well, what you do in the best of fit calculation, these expected values here, if it's for chi-squared, you'd put values from the chi-squared distribution here. Then you'd use the observed values that you collected. And it would tell you, if you get something, if you say this is statistically significantly different, and this is for a chi-squared, then you'd say it does not belong to a chi-squared distribution. If you found out it was statistically insignificant, then you could say that if it's statistically insignificant, it means the observed value is statistically insignificant from this expected value. And if this is from chi-squared, that means that, yes, this data fits the chi-squared distribution. So if you want to think about it in terms of p-value, if your p-value is above 5%, that would be a good thing because it says this data belongs to that expected value. So if this was chi-squared values and the p-value was below 5%, was above 5%, you would say it comes from a chi-squared. If the p-value was less than 5%, that means there's a difference, and it means this data does not belong to the Poisson distribution. Of course, you could also do the same thing, put binomial data for the expected value. Okay, binomial for the expected, then put in your observed values, and again, if the p-value is greater than 5%, you'd say, yes, this comes from a binomial distribution. If the p-value is less than 5%, you'd say that it's different. It doesn't belong to the binomial distribution. And this is why they call it the best of fit, chi-squared best of fit, because you can take your raw data and see what distribution it most likely belongs to. It's a very powerful test and used very often for those types of situations where you need to know what kind of distribution you're working with. So again, that's why they call it best of fit. Well, hopefully that was helpful. If you have any questions, feel free to contact me. Remember, we offer a lot of different preparation courses for ASQ, American Society for Quality, a wonderful organization. And I have a website for all our various classes here. If you want to put this video on pause, maybe take a screenshot, you can pick the website of interest. It'll take you to that class and tell you all about it. Wonderful classes. We've been preparing students for many decades now, almost 3, and we've become very good at helping students prepare for ASQ certifications. So please keep us in mind. Hopefully you learned something new today that will help you. If you found something that is helpful, please push your thumbs up button or like button. It would be greatly appreciated. Thank you, and have a great day. Goodbye.